Well, it's wonderful to be here on such a beautiful, beautiful day, talking to everyone here. I've been asked to talk about methane because, that's what cows do. And I have a farming background in my family as well. My brother, who might be in the back, would be surprised to remember that our mother actually ran a dairy for a while, a long time ago. He might not remember it, but I do. It comes out the front end of the cow. And as Deputy Gita said, it's perfectly natural. It's been around for cows. It's not just cows. It's all the foregut ruminants, the cows, the antelope, deer, and so on, and pseudo-ruminants like hippopotamuses as well, which ruminate in the front, and then methane comes out. You can do things, but it does come out. Some comes out the back end, and some comes out of the back end of about 1 in 6 humans as well, and occasionally from horses. But that's rather less. So it's the front end of the cow. And here's some volunteer cows in Zimbabwe helping us. And cows are always keen to volunteer. No cows were harmed in the making of this science. Right, and here's some of Andrew's cows volunteering equally well. Jersey cows are just as keen to come and help. They're breathing into a little pipe, we're then pumping the air back, and then we take that into our laboratory and we analyze that. Oh, sorry, I'm going to be talking about methane's important, where we are with methane, how we identify where the methane comes from by using the carbon isotopes. I'll talk about that in a moment. And then where it comes from, natural wetlands are the biggest source. Then fossil fuels, then agriculture, and then I'll talk a bit about the breath of cows and manure, and all these trade-offs about how do we deal with this problem. Okay, why is it important? Now, you can't read that because this is the Intergovernmental Panel on Climate Change draft report, which is coming out. I'm allowed to quote it now. It was under tight embargo before that. The top bar on the left-hand one is the climate warming due to carbon dioxide. The second bar down with 3 colors, a sort of brown and green, that's the climate warming due to methane. The right-hand column is the same thing. The first one's in watts per square meter, the other one's in degrees centigrade. And you can see that CO2, yeah, that's the big one. But methane's pretty important. And this is the extra that's been added to the atmosphere. We have samples of the air in snow and ice that actually go back 500,000 years or so, or more, in snow and ice in Greenland and Antarctica. So we've got a very good back record. The actual observational detailed record starts around about 1980, where it's been measured in very careful detail. 1960 actually, the original measurements. So you can see methane is really important in the effective global warming that's happened just in the last quarter of a millennium. Oh, there's another gas down there, N2O, the next one down, laughing gas. And that's linked up very heavily with nitrogen fertilizers. So the problem is often that if you reduce methane, you push up the N2O. And that's a much worse gas, actually. Now, methane, it depends on the time scale. Methane lasts in the air for 9 to 10 years, and then it's oxidized, it's CH4, add oxygen, and you'll get H2O and CO2. So it becomes CO2. Methane's a much stronger greenhouse gas, but there's far less of it. And of course, it converts. So it depends on the time scale. Over 1,000 years, it's pretty much got the same warming effect as CO2 because it just, most of that time it's CO2. It's 990 years CO2, 10 years methane. But if you're talking over, say, 20 years or 100 years, then over 20 years, it's about 86 times the warming impact. So 1 gram of methane is equal to 86 grams of CO2. If you're talking over, say, 100 years, it's about 34 times the warming impact. So 1 gram of methane is equal to 34 of CO2. And it depends on the timescale you're thinking of. And we tend to be thinking of timescales of 20 to 100 years. We're thinking about our own lives and our grandchildren's lives. Okay, if you worry about the Paris Agreement, when people first said we're going to try to do something here, that flat line there is more or less the Paris Agreement. And these are the various gases, and the one with holes in it, that's carbon dioxide, which is sort of on line with expectations because nobody expected anything, at least not by now. But the bluish one is nitrous oxide, and the green one is methane, CH4. And you can see methane is the gas that was most out of line with the expectation of the Paris Agreement. The reason it's out of line is because Paris actually expected a lot out of methane and nothing was done. So, whereas, of course, the various global recessions and goodness knows what have had huge impact on the CO2. CO2 is growing, and CO2 is the big problem, and it's growing almost inexorably. But in comparison with the expectation, it's actually almost a bit below the expectation. It was thought to be even worse. So that flat line there is not level progress. It isn't. It's the expectation, which was steep growth. It's just methane is above that. Okay, so here's a couple of little plots. Methane, back before humans started running around, let's say 10,000 years ago, was about 750 parts per billion of the atmosphere. If you have 1 billion liters of atmosphere, 750 of them would be methane, right? Or put it another way, it's 0.75 parts per million. That's about where it was. Imagine you're driving down the motorway at 75 miles an hour. That's what it was. The Romans come along, and Roman Empire, it goes up to about 1 part per million or 1,000 parts per billion. And then all sorts of strange things happen. And methane actually grows much faster, particularly with the coal industry, than CO2. And by the year 2000, it was around about 1780 parts per billion, or 1.78 parts per million. And then it seemed to stabilize. It's almost as if we're driving down the motorway at 178 miles an hour, got our foot flat down, but that's where we're going. We're not going to go any faster. And everyone thought, oh, thank goodness for that. And in this bottom diagram, that's the carbon has two stabilized tips, carbon-12, which is most of us, 99% of us, and carbon-13, which is 1%. And geologically sourced methane, that's from coal and natural gas, is rich in the carbon-13, which on this bottom panel is going upwards. Biological methane, which comes from cows and wetlands, is richer in carbon-12, and that's downwards on that graph. Okay. And for 200 years, the methane, you can get this from bubbles and ice cores, had been going up in this bottom panel. Until about 2000, when it stabilized and everything went flat, we thought, okay. And then suddenly something happened in 2007. And methane started going up. And this bottom panel, the 13 content, started going down. What's the explanation of that? Well, there's a big new source of methane, and it's biological, because it's richer in carbon-12. There are other possible explanations, but that's the most likely one. And this trend has increased. This goes to 2016. It's actually getting worse, and this graph at the top here is actually accelerating upwards. It's almost as if instead of going at 178 miles an hour, we're now going at 195 miles an hour, and we'll pretty soon get to 200 miles an hour. Yeah, that's not a stable situation to be in. And it's been driven by this transition to sources that are richer in carbon-12. So something's happening. Well, this is what we call the isotopic seesaw. The methane in the air is somewhere around, don't let the minuses worry you here too much. I lived in Saskatchewan where minus 40 was a normal average temperature in winter mornings. Minus 50 is about where the air is. The minuses are to do with the calibration. If the methane comes from biological sources, which is essentially anaerobic microbes called methanogens. They exist where there's no oxygen, where all the oxygen's been taken up by other things. So it's a cow's tummy or a wetland. Then it's very light, and that will tilt the seesaw to the left. If it comes from fires or fossil fuels, these are rather heavier, that tilts the seesaw to the right. At the moment, the trend is to the left. So something that's sources on the left-hand side is causing this recent rise in methane since 2007. And it's a very fast rise. Back in the 1980s, the rise was tilting the other way. That was the Russian gas leaks and the huge coal industry increases in Russia. So how do we find out? Well, we're measuring. This is our measurement station in Spitsbergen. You stand there and you can almost touch the North Pole. We measure in Ascension Island, which is close to the equator. And we've got a collaborative group of stations around the world which are measuring. And our Moya project, which I've been running, is the UK's Global Methane Project, has been measuring in Africa and South America. We kidnapped the British Antarctic Survey's aircraft and put them down in Bolivia to measure Amazonian methane, big wetlands, measuring in the Falklands, measuring all around the place, trying to figure out what's going on. So here's some of our equipment. This is our much-loved little aeroplane. It's the facility for airborne atmospheric measurement, the farm plane. It's the UK's research aircraft. As you can see, it's a very tough little jet, which can go all sorts of places. Then that's our own lab's vehicle, which is coming here next week. Actually, that's the earlier vehicle. And then you can just go along to, these are water buffalo, actually, in Hong Kong. The blonde one there, Boris, was very helpful. He was a big bull and kept blowing, and you can see his big blonde hairstyle. Mostly cattle are lovely. So this is our plane in Africa. This is our team in Dakar in Senegal, and flying over fires in Senegal forests. This is where rosewood is coming from. There's a huge amount of illegal cutting. That's inside the plane. The poor woman standing up there at the cockpit door in a four-way harness. This is just before we hit an enormous bump, the career best bump for the ex-RAF pilot. And she was in a four-way harness. She didn't hit the roof, thank goodness. It's quite exciting in that plane. Okay, global budget. Who's making this stuff? It's about 600 million tons a year that's dumped in the air. Now, methane's a perfectly natural gas. And way back in the Precambrian, it was probably the thing that kept the oceans liquid. It's very ancient. It's biologically made. It's a really important part of nature, as we were told earlier on, just now. 600 million tons. A bit short of 200 million tons come from wetlands, especially the tropical wetlands, Amazonian wetlands, African wetlands, Indonesian wetlands, but also the boreal wetlands that's up in Canada and Siberia. I took this photo in Canada. You can see this tree's been cut down by a logger. You notice the height of that? That's the height of a beaver's mouth. Beavers are magnificent loggers. They're monster methane makers. And they cut down trees, and then they drag them into the pond. It rots and turns to methane, which is how beaver lives in the winter. They eat the tree leaves and the tree bark. So wonderful animals. Yeah, you can see the cut that this one's been making here. They don't appear to know where the tree's going to fall, but they stand there and the tree falls. And if you're lucky, the beaver doesn't get killed. Wonderful animals. Okay, so that's wetlands. Now, a cow is a walking wetland. It's a walking tropical wetland at 37 degrees, whereas the tropical wetlands tend to be 31, 32. But it's pretty much the same thing. Then there's the fossil fuel industry. Natural gas is primarily methane. Any gas leak is methane leak, and it's a waste. Coal mines, they blow up if you have too much methane. And also the oil industry tends to flare it if they don't want the methane. They don't want the gas, they just want the liquid stuff. Fires as well, crop waste fires all over Africa, and also grass fires. And then waste as well, landfills. Huge emissions, more and more in the tropics. And then we come to the ruminants. And they're responsible for a bit over 100 million tons. So rather less than the fossil fuel industry, but in that same sort of order. So we've been looking, this is the Bangweulu wetlands in Zambia. You've never heard of them, but they're one of the most beautiful wetlands on Earth. It's where David Livingstone died. It's also where the First World War ended, and today's Remembrance Day. It ended in Zambia, when the German army laid down its arms. I think it was the 14th or 15th of November in Zambia. They were attacking Lusaka. So it's a fairly historic place, and Bangweulu is symbolic of what's happening in the tropics. As climate warms, the tropics become more active, and they're also meteorologically expanding. And when wetlands get wet and get hot, they make more methane. And there's a feedback going on there. Warming, feeding, warming. Methane comes from the natural gas infrastructure in particular, and in the UK that's responsible for a lot of emissions. All sorts of things, pipelines, gas governors and so on. Every bit of the industry is leaking. Some bits leak more than others. These gas governors, which are sort of distribution centers, they leak quite a lot. In America, we all know about fracking. Actually, the frackers are getting a lot better, mostly. Biodigesters in Britain are probably worse than frackers, or as bad. So this is our vehicle. We drive around, and we'll be bringing this to Jersey next week. It's basically just a vehicle with gadgets on top, which measure the wind, suck in air, and then the GPS tells you where you are, so you can map. Anyone who reads the Financial Times, I'm sure you guys are all Financial Times readers, we made it onto the front page of the FT last week because we found a big gas leak just opposite the COP26 conference. At the Rangers Stadium, if anyone knows Glasgow, and of course the husband of our the person who was driving is a Celtic supporter. He was quite pleased by that one. Okay, so here's our gadget, and it's basically a car stuffed full of a lot of equipment. That's all you need to measure, and we're having a lot of trouble importing it into Jersey, actually. One of the problems of doing the science is you can't take these instruments to the tropics. Most countries will say you can't bring them in because the customs duties are so complicated. And it's quite difficult. That's why we go places like Ascension Island, where you can actually get the wind to bring the air to you. And so we use the wind as a sort of telescope. We run the Met Office forecast backwards. And so here in Jersey, we have colleagues in Paris, and the air that crosses Jersey is the background for Paris, for example. It's potentially a very important place here because you can get the background for France. So you measure in France and you measure here, and the difference is the added bits on the trajectory between here and France. So we've been mapping London, and one of our graduate students has driven all the major streets in London, and all these dotty things, that's where the leaks are. It's quite simple. You just need to put a sticking plaster on those leaks. Not difficult. Drive around landfills. The UK has actually done a very good job on landfills, better than almost any other country on Earth. But landfills are very big emitters. And never mind the calibration. Basically, the height of the peak is how much methane's there. This is a landfill in southern Britain. And you can see where the leaks are. Now, to cure that, all you need to do is to put 20 centimeters of soil on top. Because soil then hosts bacteria called methanotrophs. A troph is an eater, so it's methane eaters. And they eat the methane. And 20 centimeters of soil will eat up most of methane almost anywhere, provided it's aerated, moist soil. Forests that these trees around here, underneath them, is probably eating methane. As the low and high pressure fluxes air through the soil, then the methane is taken up by the soil bacteria. So a bit of soil, that's all you need. And tropical landfills are probably very big emitters because they're mostly uncovered. Okay, now let's get down to the cow. Now these are some of my favorite Swiss cows. I worked in Switzerland for a while and fell in love with Swiss cows. They're rather sweet. Our group, I wasn't with them, but our group went out to Queensland and Australia. We work with the University of New South Wales. And in Queensland, there's a very big coal seam gas industry, extracting gas from the coal seams and shipping that off to Japan and various other places. And right on top of it is a big beef industry. And this is Beef City, which is a particular feedlot with 22,000 animals in it, or at least when mapped around it. And you can see the peak there. The gas fields, actually, the individual extraction sites, there might be some here. Some of these might be gas sites, I'm not sure, was fairly flat. But then just look at that peak. So the question is, how can we do anything about this? The answer is perhaps yes. This is the Cambridge Vet School cows. You can tell these are not Jersey cows. They've got a herd of black and whites. And we're trying to work out just where the methane is in this barn. And of course the answer is some parts of it have circulating air and it's almost background. Other parts, there's a lot of methane. And the question is, if there's a lot, can we do something about it? And the answer is probably yes. You might recognize that. Is Andrew here? It's an excellent cap. So here's our helper and this magnificent manure drone that's going up and down, cleaning the place up. One of the big sources of the methane emissions is actually the manure itself. Because in a tank, or in America, they have what they call manure lagoons. Very rapidly, all the oxygen is used up, and so it goes anaerobic. And then the methanogens get to work, and they make methane. And there you'll get methane coming off very high concentrations. Where there's high concentrations, you can do things with removing that methane. So to reduce methane, the first thing to do with reducing emissions is just to stop them being emitted. The most obvious thing is to stop the gas leaks. That's an incredibly stupid thing to do, to leak gas. I would love to shut down the world's coal industry, which I think will happen in the fairly near future, including eventually steel. Steel, I think, uses about 1/7 of the coal. I'm not sure, I may be wrong on that. You need carbon to take the oxygen off iron ore. You can replace that with hydrogen. So that's a longer term thing. But coal-fired electricity is becoming uneconomic right around the world. It's cheaper to go solar or something like that. Problem with solar, of course, is you only get that when there's sun. The gas industry in the near future, I'm talking the next 10 years or so, is primarily concerned with producing electricity nowadays. We distribute gas to every home. I think in the fairly near future, we'll probably stop doing that. I'd like to see them putting, I don't know, internet wires or electricity wires or something down all those gas pipes. There is a suggestion of putting hydrogen into gas pipes to people's houses and boilers. I suspect that's a bit dangerous because hydrogen is very, very leaky. It's an indirect greenhouse gas because it has effects on air chemistry. And it also has bigger impacts on air pollution. And we haven't really thought that through. There's a group think saying hydrogen for electricity generation or as a store of energy maybe, but to put it down a gas pipe, I'd be very cautious. And then when it comes to methane, biodigester leaks and landfills, particularly tropical landfills, are just crying out to be stopped. And may be profitable with certainly biodigesters, you get more gas off it. You know, gas leaks are stupid. It's just bad management. But then you get to the more complicated issues of agriculture. Most of the ruminants in the world are in the tropics or the subtropics. The country with the world's largest population of cattle is India. And I have Indian relatives. You know, many parts of India, half the food comes from cattle. And they're acquiring food from pasture land that you can't plough up. Take away the cattle, people starve. That's true in Africa, Ethiopia, the whole belt of Central Africa, very, very big cattle populations. And most of the people get their food from the cattle, from pasture land. Then there's manure. And then, particularly in Africa, there's crop fire burning, and India too, which is a huge cause of air pollution. And we really need to get away from that. And a big source of methane too. So that's the sources of methane. Now, are there ways in which you can actually remove methane? And there are targets. Now, ambient air has about 1.9 part per million methane, or 1900 part per billion. It's not really worth removing that. But if you get air that's 1% methane that's almost going to explode, it'll explode at sort of 4 or 5%, then yeah, you really do want to take that out. And somewhere in the middle here, there's some transition where it's probably worth taking the methane out. And number 3 there, were high methane air, about 100 part per million. That's what you might get in a cattle barn. And then it might be worth taking out. This is a sort of calculation of different, there's a lot of detail on here, but different energy costs. You know, where does your energy come from? Does it come from mining coal, or does it come from wind or solar power? And if your energy is from wind or solar power, it's probably worth taking out 100 part per million methane. It's not worth taking out methane just directly from the air, which gets oxidized anyway by sunlight. But it is worth taking it out if it's in the barn, if there's a lot of it. So, how do you reduce emissions from cattle? You can probably change the diet, but then there's all sorts of loops in there. You might reduce the amount of methane being emitted, but then you may need to have more cattle or other things happen in whatever that product is. But you probably can remove some of the methane from the air there, particularly from around manure. There are various ways of removing methane. The simplest one is just to pass the methane over a hot metal catalyst, iron oxide or copper oxide. You'd have to recapture the energy by passing the exhaust around the air as it comes in. But you could do that. And we've got a gadget in our lab that's been running for 20 years doing exactly this. This is what submarines do when they clean the air in the submarine. Another way is to paint your roof with titanium dioxide paint. You need an awful lot of square meters of roof, so it's not very big, but since most roofs are already painted white, you can probably take out a fair whack of methane that way, particularly in the tropics. And then you get biological removal. Here's just a sort of concept. You've got a lot of cattle in a barn. You pump the air out from underneath the noses of the cattle, under the feeding troughs, and you pump it through soil in a greenhouse next door, and then the methanotrophs just eat the methane, and you grow some tomatoes on top. That probably would work. There are other methods. You can pass the methane through columns filled with a mineral called zeolite, which should also take it out. So there are ways in which you can take methane out. And if the air is quite rich in methane, it's probably worth doing, and it's probably quite cheap. So there are trade-offs here. On a global scale, though, if we entirely went vegan, most of India and Africa would probably starve because the pasture land here is feeding them. And if you don't do that, you've got to do incredible things with increasing crop production, with fertilizers and cutting forests. Too much detail on this slide. It's a very complex issue. And it also involves sheep, of course, and wool. You know, do we abandon wool? And the argument is that sheep are actually very good for pastures in many places. So I'm going to end here just saying it's not a simple problem. But we can do probably quite a lot in removing the methane from the air, where you are. We have to be very careful if we switch to crop-based substitutes, because you need to look at the full cycle. Where does that come from? Very intuitively, organic dairy is probably a decent way to go. It's better than the alternatives. That's intuitive. Can't put numbers behind that yet. So the words of Delphi, Methane, moderation in all things is probably the way forward.